Did you know we get to see the sun about 2 minutes before the actual sunrise, and it's still visible about 2 minutes after the actual sunset? And also, the sun looks pretty squashed during the sunrise or sunset. So, why are these things happening? Well, the short answer is because our atmosphere refracts light. So, in this video, we'll explore this in detail. So, let's start with something that we already know. We might already know that the Earth keeps spinning around its own axis, and that's what causes the day and the night. But since we are also spinning along with the Earth, we don't see that. Instead, from our perspective, it feels as if it's the sun. This is the sun, and the sun is very far away. That's why it's looking smaller to us. But from our perspective, it looks as if it's the sun that's going around us, and that's why we use the word sunrise and sunset. But at what position does the sun appear to be rising for us? That's what we are interested in, right? We want to know what happens at the sunrise or the sunset. And you may also know the answer to this. You may already know that when things are below the horizon, we don't see them. And when things are above the horizon, we do see them. Which means when the sun just hits the horizon, somewhere over here, that's when we see it rising. And horizon is just a tangent line that we draw to our Earth's surface. Notice, a tangent line that we draw to our Earth's surface at the place where we are standing. Okay? And so when things are below it, like right now the sun is below that, we can't see it because if we try to draw any rays of light from the sun, let's say we try to draw rays of light from the top of the sun to the point where we are standing, then these rays of light will not reach us. And the reason is because they're going to hit somewhere over here. So when any object, let's try to draw this. It's not very accurate, but you can sort of see it, right? When any object is below the horizon, any ray of light from there cannot reach our eyes because it's going to hit somewhere over here. And that's why right now the sun is not visible to us. And what would we be seeing right now? Well, we would be seeing something like this. We don't see the sun because the sun is not visible. And for us, the horizon is the part where the sky and the land or the ocean meets. So this represents the horizon for us. So right now the sun is below the horizon. And when say the sun comes somewhere over here, now the sunrise has happened. So what we would see is the sun has just started rising like this. Now so far, we didn't talk about the atmosphere of the Earth. So let's bring the sun back down the horizon. And let's say here is our atmosphere. And let's again draw a couple of rays of light from the top of the sun. Let's zoom in and look at this. So these rays of light would have, if it wasn't for the atmosphere, these rays of light would have just gone straight and they would have missed our eyes and we wouldn't be able to see the sun like we discussed before. But now, these rays are entering from vacuum into our atmosphere. And as a result, the rays of light, the light is going to slow down because light has the fastest speed in vacuum. When it enters into any other medium from vacuum, it's going to slow down. And because it's going to slow down, if we draw a couple of normals over here, this light will bend towards the normal. So if you see the refracted light, these are a couple of normals. Notice the light has bent towards the normal because it has slowed down. And if you're wondering why are the light bending towards the normal if they slow down? Well, then we've talked a lot about this in previous videos on refraction. So if you are not clear about this, it'll be a great idea to go back and watch that video and then come back over here. But now what's important to see is that these rays of light have bent down, and so they will reach our eyes. And so to understand what we see now, we have to just backtrack these rays. So it appears to us as if these rays of light are coming from, let's zoom out now, are coming from somewhere over here, and as a result, we will feel as if the top of the sun is somewhere over here. And as a result, we will see that sun somewhere over there. So that sun will look somewhere over here. And so notice, even when the sun is below the horizon, because the rays of light are bending towards us, we see the sun above the horizon. In other words, In other words, even before the actual sunrise, we see the sun has risen. So because of the atmosphere, the sun is actually below down over here, but because the rays of light are bending towards us, right now we are seeing the sun somewhere over here. And that's why we say that the sunrise, we get to see the sunrise even before the actual sunrise. And similarly, this also explains why we get to see the sun after the sunset. Once the sun has set, which means it has gone below the horizon, because the light bends and appears to reaches our eyes, because of that we still get to see the sun. And that's why the sunrise happens earlier and the sunsets are always delayed. And if you're wondering exactly how early or how delayed we see the sunrise or the sunset, then if we do the calculation, it turns out it's about a couple of minutes. So the sunrise, we get to see the sunrise a couple of minutes earlier, and the sunset will be delayed by a couple of minutes. So long story short, due to our atmosphere bending the rays of light towards us, downwards towards us, the sun appears higher in the sky. And this is not just for the sun. It will happen for any celestial body. So for the moon or the planets or even the stars. And by the way, this effect is the strongest when the objects are near the horizon. Again, if we zoom in, we can see that only when the objects are near the horizon, that's when the incident light makes a very strong angle with the normal. And if the objects come overhead us, so let's say during the noontime when the sun is right above us, now notice the incident light is almost perpendicular to the surface, and as a result they would hardly bend, and so there will be hardly any shift in the object's position. So usually, okay, let's go back. Our atmosphere makes the objects appear higher in the sky, and the effect is the strongest near the horizon. Or to be more specific, the lower the object in the sky, stronger is the shift in the object. Of course, if the object gets too low, then eventually the light will not bend enough to reach our eyes. But in general, the lower the object, more is this shifting effect. And as the objects rise higher and higher in the sky, the shifting effect becomes smaller. And eventually, when the object is at the highest point in the sky, right above us, the shifting effect is almost zero. And this also explains why sailors in the earlier times who used to use the location of the stars to navigate around would not look at the stars at the horizon for their navigation because of the same reason. Because the stars which are very close to the horizon have a huge shift in their position, and so that would cause a huge error in their navigation. All right, so the last thing is, why does the sun appear squashed during the sunrise or the sunset when it's close to the horizon? The concept is exactly the same. So can you pause and try and think about this for a while? All right, let's see. Now we know that the sun is actually below the horizon, and due to the atmosphere, it appears higher in the sky. But remember, the effect is stronger as the objects are lower and lower in the sky. We just discussed that. Lower the object, stronger the effect. Now the bottom part of the sun is lower in the sky compared to the top part, isn't it? Because the bottom is lower. And as a result, the bottom part of the sun will shift a little bit more, or it will appear a little bit higher in the sky than the top part. So the shift is not the same. So if the top got shifted this much distance, the bottom will not get shifted the same distance. The bottom might get shifted a little bit more, and as a result, that sun will appear squashed to us like this. And this is the reason why astronomers hate to take photos of celestial bodies when they are close to the horizon.